This review paper explores data-driven approaches for acoustic-to-articulatory inversion, or AAI, which is a method to estimate how speech sounds are produced by the articulators, like the tongue, lips, and jaw, based on the acoustic signals from spoken words. The paper focuses on relevant studies published between 2011 and 2021, selecting works based on several key criteria to ensure a comprehensive overview. First, it categorizes AAI into two main types: speaker dependent, where the system is trained and tailored to a specific individual's speech patterns, and speaker independent, which aims to work across different speakers without customization. The objectives of these studies vary, including approximating articulatory movements to visualize how speech is formed, selecting the right articulatory feature spaces for analysis, and applying AAI to automatic speech recognition systems. Other goals involve exploring the correlations between acoustic features, like sound waves, and articulatory features, such as the positions of the tongue or velum, as well as developing frameworks for computer-assisted language training. The paper also examines the corpora used in these studies, which consist of simultaneously recorded speech, audio, and medical imaging data. This includes techniques like electromagnetic articulography, which tracks the movement of articulators using sensors, electropalatography, which maps tongue contact with the palate, laryngography, and electroglottography, which measure vocal fold vibrations, X-ray cineradiography for detailed imaging of the vocal tract, ultrasound for real-time views of tongue shape, and real-time magnetic resonance imaging, or RTMRI, which provides dynamic pictures of the entire speech production system. These datasets are crucial because they link what we hear in speech to the physical actions that create it. In terms of methods, all the reviewed works rely on machine learning techniques, reflecting the shift toward data-driven models in recent years. These approaches use algorithms to learn the complex relationships between acoustic inputs and articulatory outputs, often involving neural networks or regression models to handle the intricacies of speech data. For evaluation, the paper notes that AAI is fundamentally a nonlinear regression problem, meaning it's about predicting continuous articulatory positions from discrete acoustic data. Researchers assess performance using metrics like the correlation coefficient, which measures how well predicted and actual articulatory movements align, root mean square error, which quantifies the average error in predictions, mean square error, a similar measure of overall discrepancy, and mean formant error, which specifically evaluates errors in formant frequencies, the resonant peaks and speech sounds that relate to articulatory configurations. Human speech production is a multi-step process that begins with the initiation of an airstream from the lungs. This air then moves through the larynx during phonation, where the vocal folds add characteristics like voicing for sounds such as vowels or voicelessness for sounds like S or F. Next, the oronasal process involves the velum, a soft tissue in the roof of the mouth, which directs the air either through the nasal cavity for nasal sounds like M or in, or through the oral cavity for other sounds. Finally, articulation shapes this airstream by adjusting the place and manner of articulation, such as bilabial sounds made with the lips or plosive sounds involving a complete closure and release. The core of AAI lies in uncovering the relationship between these articulatory actions and the resulting acoustic signals. It's defined as a nonlinear regression task that infers articulatory trajectories, essentially the paths and positions of articulators over time, from the acoustic speech signal. For instance, from a recorded waveform of someone saying a word, AAI attempts to reconstruct how their tongue moved or their lips pursed. This is illustrated in the paper through a figure that shows how acoustic features lead to estimates of articulatory places and manners. One of the biggest challenges in AAI is its one-to-many nature. While a specific articulatory configuration always produces a predictable acoustic output, the same acoustic signal can result from multiple different articulatory states. For example, a particular vowel sound might be produced with slight variations in tongue position depending on the speaker, accent, or context, making it hard to reverse engineer the exact movements. This non-linearity has puzzled researchers for over 3 decades, but ongoing studies are working toward more accurate solutions using advanced machine learning. The practical applications of AAI are wide-ranging and impactful. In speech signal analysis and synthesis, it helps create more natural-sounding synthetic voices by incorporating realistic articulatory data. For automatic speech recognition, AAI improves systems like voice assistants by providing deeper insights into how sounds are formed, potentially reducing errors in noisy environments. In speaker recognition, it aids in identifying individuals based on unique articulatory patterns, enhancing security systems. Additionally, AAI has been applied to evaluate speech in pathological cases, such as for people with speech disorders, and even in diagnosing conditions like depression through subtle changes in speech production. A key benefit highlighted is the development of user-friendly feedback systems. For instance, AAI can generate interpretable images or trajectories of articulatory positions, especially tongue movements, which can be visualized in real time. This is particularly useful for phonetic training, language learning, and speech therapy. Imagine a system where a person with a speech impediment sees an animation of their tongue's incorrect position and gets guidance to correct it, making therapy more engaging and effective. The paper also touches on how accurate articulatory feature extraction can support pathological language and speech development. Studies have shown that tools derived from AAI can assist in early intervention for conditions like dysarthria or apraxia, where precise feedback on articulation helps patients improve. Looking at the broader scope, future enhancements in AAI could involve refining machine learning models to handle more diverse datasets, incorporating multimodal data from various imaging techniques, and addressing real-world variability like accents or emotional states in speech. This could lead to more robust applications in education, healthcare, and technology, ultimately making AAI a cornerstone for advancing speech-related research.